Part 4 introduces Agile workflows, the structured movement of work from an initial need to a completed and valuable outcome. Agile workflows help teams organize priorities, maintain visibility, and coordinate their efforts throughout development. They create a shared understanding of what needs to be achieved, what is currently being worked on, and what has been completed. For engineering teams, this becomes especially important when multiple disciplines must work together toward a common objective. A clear workflow also helps teams identify dependencies, manage changing priorities, and respond to challenges without losing direction. In this part, we will explore how Agile teams maintain a continuous and transparent flow of work from direction to delivery. Part 4 introduces Agile workflows, explaining how product intent is progressively transformed into a completed engineering outcome. First, product direction establishes the vision, goals, and outcomes that guide the team's decisions. Second, the product backlog provides an ordered and transparent view of all the work needed to advance the product. Third, user stories describe requirements from the user's perspective, connecting a specific need with the value it should deliver. Fourth, the sprint backlog converts selected priorities into a practical plan that the team can execute during the sprint. Finally, the done increment represents integrated, tested, and completed work that meets the agreed quality standards. Together, these 5 topics explain how Agile teams maintain direction, organize work, coordinate execution, and deliver value consistently. Let us now start with product direction. Product direction ensures that every engineering discipline works toward the same valuable vehicle outcome. Without a shared direction, individual teams may be highly productive, but productivity alone does not guarantee a useful or successful vehicle. For example, the battery team may optimize driving range while the mechanical team adds weight and the vehicle controls team prioritizes acceleration. Each decision may appear technically valid within its own discipline, but together they can create conflicting priorities and weaken the overall product. Product direction establishes the shared outcome against which engineering choices, priorities, and trade-offs can be evaluated. It helps every team ask, does this engineering work move the product toward its intended user and business outcome? With this common reference, teams can coordinate their decisions while still applying their specialized engineering knowledge. Importantly, product direction provides alignment without prescribing every technical solution. It defines where the product must go, while allowing engineers to determine the most effective way to get there. Product direction connects long-term product intent with everyday engineering execution. It sits above individual requirements, tasks, and engineering activities, providing a common destination for every team. The product backlog contains the ordered work required to advance toward the product goal. The capability roadmap communicates how major product capabilities are expected to progress without becoming a detailed task schedule. Project milestones coordinate significant events such as design releases, procurement, subsystem testing, integration, and vehicle trials. Within each sprint, the sprint goal defines the valuable outcome the team intends to achieve. Engineers execute the detailed work through the sprint backlog, while the product goal maintains continuity across multiple sprints. Direction and alignment flow downward from the product goal to sprint execution. Test results, technical risks, user feedback, and integration evidence flow upward, allowing teams to adapt the roadmap or even reconsider the product direction. This continuous connection ensures that engineering work remains coordinated, evidence-based, and focused on meaningful product outcomes. Turning product direction into vehicle capability begins with an outcome-oriented product goal, rather than a list of components to be completed. The goal is then broken into capabilities that the vehicle must demonstrate, such as energy storage, propulsion, vehicle control, functional safety, and integrated validation. These capabilities are arranged in a logical sequence based on technical dependencies, major risks, and integration needs. Milestones should represent meaningful evidence of maturity, such as a validated subsystem or an operational vehicle, rather than merely the passage of time. For each stage, the team creates a sprint goal that advances one or more capabilities toward the next milestone. Product backlog items and detailed engineering tasks are then selected because they directly support that sprint goal. At every review point, the team examines working evidence, test results, and integration learning. Based on this evidence, the product backlog or capability roadmap may be adapted. This approach creates clear traceability from daily engineering work to the sprint goal, product goal, and ultimately the product vision. We have now completed product direction and understood how a clear vision and goals guide the team. Let us return to our agenda and move to the next topic, product backlog. We will now explore how Agile teams organize, prioritize, and maintain visibility of the work required to achieve the product goal. The product backlog is the single ordered source of work required to improve the product. It translates product direction into visible and actionable product backlog items that teams can understand, refine, and deliver. In EV development, work may originate from customers, product management, mechanical engineering, electrical engineering, embedded software, testing, safety, compliance, or suppliers. A single shared backlog prevents these needs from becoming fragmented across disconnected spreadsheets, emails, and departmental task lists. The word ordered is more accurate than prioritized because an item's position depends on several considerations. These include product value, technical risk, urgency, dependencies, and opportunities for learning. The product backlog is not a fixed requirements document. It continuously evolves as the team receives new technical evidence, user feedback, supplier information, and test results. Items near the top should normally be clearer, more detailed, and better understood, while work expected much later may remain broader and require further refinement. An epic represents a large product outcome that is too broad to complete within one sprint. For example, reliable urban driving may require several vehicle capabilities and contributions from multiple engineering teams. A capability describes what the product must be able to achieve, such as managing battery energy or responding safely to a detected fault. A feature is a recognizable product behavior or function, such as regenerative braking or remaining range estimation. A user story expresses a smaller need from a user or stakeholder perspective and connects that need to its intended value. Epics and user stories are therefore not interchangeable. An epic may span several sprints, while a user story should be small enough to refine, estimate, implement, test, and potentially complete within one sprint. However, not every product backlog item must be written as a user story. EV development also requires defects, technical investigations, compliance activities, architecture changes, test environment work, cybersecurity improvements, and technical debt reduction. Regardless of its type, every product backlog item should describe a clear outcome, purpose, and basis for verification. Effective product backlog management is the accountability of the product owner. This includes communicating the product goal, clearly expressing and ordering product backlog items, and ensuring transparency. Although many people provide input, accountability for backlog ordering remains with the product owner and cannot be transferred to a committee. Developers contribute essential knowledge about feasibility, effort, architecture, integration, testing, risks, and dependencies. In EV development, mechanical, electronics, embedded software, controls, safety, and validation engineers all support refinement. Stakeholders add user needs, constraints, regulatory expectations, supplier information, and operational feedback. Ordering considers more than business value. Safety risks, compliance deadlines, long lead components, technical uncertainty, and integration dependencies may move an item higher. Refinement continuously clarifies, splits, estimates, and adds sufficient detail to product backlog items. It improves shared understanding but does not automatically commit an item to a sprint. A transparent product backlog exposes all work competing for the team's limited capacity. Customer-facing features must not hide essential engineering work such as fault correction, safety validation, compliance evidence, integration, and technical debt. Items near the top should have clearer outcomes, acceptance criteria, estimates, and known dependencies. Lower items may remain broader because requirements and technical knowledge will continue to evolve. Dependencies must also remain visible. For example, a low battery warning may depend on reliable battery telemetry and an accurate state of charge calculation. Cross-disciplinary dependencies should influence ordering, preventing teams from completing isolated work that cannot yet be integrated. Safety and compliance activities may be ordered ahead of customer-facing features when they reduce significant risk or enable vehicle testing. Backlog transparency helps the product owner, developers, and stakeholders understand what is planned, why it is ordered that way, and what remains uncertain. Test results, supplier changes, defects, and sprint review feedback may require immediate backlog adaptation. During sprint planning, developers select suitable product backlog items and create a sprint backlog around one coherent sprint goal. We have now completed product backlog and understood how Agile teams organize and prioritize the work required to achieve the product goal. Let us return to our agenda and move to the next topic, user stories. We will explore how user needs are translated into clear, valuable, and actionable requirements for the team. A user story is a concise description of a need from the perspective of a user or stakeholder. The commonly used structure is, as a particular user, I want a specific capability so that I receive a meaningful benefit. The persona identifies who needs the capability, such as an operator, maintainer, or integration engineer. The need explains what that person wants to accomplish without prematurely prescribing a technical solution. The value explains why the need matters and helps the team evaluate its priority. For example, an electric vehicle operator may need reliable remaining range information to make safe journey and charging decisions. However, a user story is not a complete specification or a substitute for detailed engineering documentation. It provides a starting point for conversations about expected behavior, technical constraints, system interfaces, risks, and verification. Acceptance criteria then define the observable and testable conditions that must be satisfied before the story can be accepted. Together, the story and its acceptance criteria connect user value with a clearly verifiable engineering outcome. Product direction establishes the broader outcome that the organization intends to achieve. Epic's capabilities and features progressively organize this direction into smaller areas of product value. User stories express specific needs that can be discussed, refined, and potentially completed within a sprint. Once identified, a user story becomes a product backlog item and is ordered alongside defects, risks, compliance work, and technical improvements. During refinement, the team clarifies its acceptance criteria, dependencies, technical constraints, and approximate effort. During sprint planning, developers may select a sufficiently understood story when it supports the sprint goal. The sprint backlog then contains the mechanical, electrical, software, integration, and testing tasks required to deliver it. A story is complete only when its acceptance criteria and the team's definition of done are satisfied. Technical investigations, defects, compliance activities, and other engineering work may require formats better suited to their purpose and verification needs. The product owner is accountable for ensuring that product backlog items are clearly expressed, properly ordered, and transparent. User stories may be proposed by different people, but they should be refined collaboratively. Operators, maintainers, customers, safety specialists, and integration teams provide essential operational context and constraints. Engineers or developers contribute technical knowledge about architecture, feasibility, effort, interfaces, risks, dependencies, and verification. Acceptance criteria define the specific conditions under which the intended behavior can be accepted. Acceptance criteria apply to the individual story, while the definition of done establishes broader quality expectations for completed work. The Invest checklist helps the team assess whether a story is independent, negotiable, valuable, estimable, small, and testable. In practical terms, the story should be sufficiently independent, open to discussion, valuable, understandable enough to estimate, small enough for a sprint, and possible to verify. The Invest checklist helps Agile teams assess whether a user story is ready for meaningful discussion, estimation, and delivery. Independent means the story should avoid unnecessary dependencies that could prevent completion within the sprint. Negotiable means the story encourages conversation about the best solution, rather than prescribing every implementation detail too early. Valuable means the story delivers a meaningful outcome for a user, stakeholder, or product. Estimable means engineers or developers understand the work well enough to assess its approximate effort, complexity, and risk. Small means the story can reasonably be completed within one sprint. Testable means clear acceptance criteria allow the team to verify the intended behavior objectively. For example, an EV low battery warning should provide measurable operator value, remain small enough for delivery, and include testable warning conditions. However, Invest is guidance for improving story quality, not a rigid approval gate that replaces engineering judgment and team discussion. Effective user stories begin with personas representing people or stakeholder roles with meaningfully different needs, not merely organizational departments. An operator may need a clear low battery warning early enough to respond safely. A maintainer may need stored fault codes and operating data to reduce diagnosis time. An integration engineer may require a stable, documented battery data interface for reliable use by vehicle control and display systems. Functional requirements describe what the system does, such as displaying state of charge, issuing warnings, or recording faults. Non-functional requirements define qualities and constraints, including response time, accuracy, reliability, cybersecurity, environmental tolerance, and availability. These conditions may become story-specific acceptance criteria or broader quality requirements across multiple stories. Large stories should be split when they cannot be understood or completed within one sprint. They may be split by workflow step, interface, user role, data state, exception path, or increasing capability. Avoid splitting only into database, embedded software, and user interface layers when none delivers independently verifiable value. Every smaller story should produce a meaningful outcome or validated learning. We have now completed user stories and understood how user needs are translated into clear, valuable, and actionable requirements. Let us return to our agenda and move to the next topic, sprint backlog. We will explore how selected work is organized into a practical plan for the sprint. The sprint backlog is the developer's working plan for achieving the sprint goal. It connects three essential elements: the sprint goal, the product backlog items selected for the sprint, and an actionable delivery plan. The sprint goal gives the team a common purpose and guides decisions when conditions or priorities change. The selected product backlog items define the valuable outcomes that the developers intend to complete. The delivery plan translates those outcomes into activities such as design, procurement, development, integration, testing, documentation, and compliance. In EV development, delivering one feature often requires coordinated mechanical, electrical, electronics, embedded software, and validation work. The sprint backlog makes these activities and their connections visible to the entire team. However, it is not a frozen task list created only during sprint planning. Developers continuously update the plan as they discover new work, dependencies, risks, and better implementation approaches. Changes to delivery plan are acceptable throughout the sprint, provided they continue to support and do not endanger the sprint goal. The product backlog contains all visible work that may improve the product. During sprint planning, the entire Scrum team collaborates to establish a valuable and achievable sprint goal. The product owner explains priorities and desired outcomes, while developers consider capacity, feasibility, effort, risks, and dependencies. Developers then select the product backlog items they believe they can complete while achieving the sprint goal. These selected items enter the sprint backlog together with an initial engineering plan. As understanding improves, developers decompose the work into clear, actionable tasks. For a low battery warning, these tasks may include battery data acquisition, state of charge thresholds, warning logic, operator display changes, and vehicle level testing. Mechanical, electronics, software, and validation work must come together as one integrated behavior, not remain as separate departmental outputs. The resulting increment must satisfy the story's acceptance criteria and the team's definition of done. Any unfinished or unverified work does not automatically become part of the completed increment. Engineers or developers are collectively responsible for creating, managing, and adapting the sprint backlog. Individual task ownership makes responsibility visible, but delivery accountability remains with the developers as a team. A task owner coordinates the activity, while collaborators contribute the knowledge required for completion. Tasks should be small enough to reveal progress and support coordination without creating excessive administrative detail. EV development frequently crosses subsystem boundaries. A low battery warning may require battery management data, communication signals, warning logic, display behavior, harness verification, and vehicle-level validation. Mechanical, electrical, and software tasks must therefore expose their physical, power, signal, data, and timing interfaces. During the daily scrum, engineers or developers inspect progress toward the sprint goal and adapt their plan. New work, change estimates, dependencies, and blockers must be reflected in the sprint backlog. A blocked task should remain visible and trigger coordinated action rather than silently waiting with one engineer. A Kanban-style task board visualizes the work contained within the sprint backlog. It does not replace the sprint backlog, but provides a practical view of its actionable plan. The columns show work progressing from planned activity through execution, review, testing, and completion. Each card identifies the task, responsible engineer, collaborators, and relevant dependencies. Work in progress limits prevent the team from starting too many tasks simultaneously. When work accumulates in review and test, the team should help complete verification before beginning more work. Blocked cards need a clear visual indicator and an identified impediment. For example, testing unavailable battery data may remain blocked until the battery management simulator supports signal loss conditions. Developers update the board as work changes, tasks emerge, blockers arise, or collaboration becomes necessary. A task enters done only after all agreed checks are complete. The integrated outcome must satisfy its acceptance criteria and the definition of done. We have now completed sprint backlog and understood how selected work is organized into a practical plan for the sprint. Let us return to our agenda and move to the final topic, done increment. We will explore how completed work is integrated, tested, and verified against the agreed quality standards. An increment is a concrete and usable step toward achieving the product goal. Each increment builds upon and remains compatible with previously completed increments. In EV development, separate outputs from mechanical, electrical, electronics, and software teams do not automatically form an increment. For example, a low battery warning becomes useful only when battery data, communication, warning logic, display behavior, and fault responses operate together in the vehicle. Work cannot become part of the increment unless it satisfies the definition of done. Statements such as development complete, testing pending, or documentation to follow clearly indicate unfinished work. A done increment must be usable and potentially releasable. The organization may decide when to release based on operational or commercial considerations. More than one increment may be created during a sprint, but every increment must remain compatible with earlier work. Together, they must form a coherent, integrated, and usable product state. Scrum associates a specific commitment with each of its three artifacts. The product goal is the commitment for the product backlog and describes the future product state the team is working toward. For an EV, this may mean achieving safe and dependable mobility. The sprint goal is the commitment for the sprint backlog and gives the team a common purpose for the current sprint. A related sprint goal could be demonstrating a reliable low battery warning under defined operating conditions. The definition of done is the commitment for the increment and establishes the required quality state of completed work. It defines the common engineering checks required before the low battery warning can become part of the increment. These may include integration, reviews, testing, documentation, and traceability. Together, the three commitments clarify where the product is going, what the current sprint intends to achieve, and what completion means. Scope and implementation plans may be adapted during the sprint, but quality must never be reduced simply to declare the work complete. Acceptance criteria describe the specific conditions that a product backlog item must satisfy. For a low battery warning, they may define the activation threshold, display behavior, update timing, and response when battery data becomes unavailable. The definition of done establishes the broader quality conditions that completed work must meet consistently. These may include design review, code review, integration, testing, and documentation. Passing the acceptance criteria alone does not make the work done. Similarly, following the engineering process does not prove that the required user behavior has been delivered. The work must satisfy both its acceptance criteria and the definition of done. When multiple Scrum teams work on the same product, they must follow a mutually consistent definition of done for the combined increment. A definition of done must be demonstrated through objective evidence rather than personal assurance that the work is complete. For a low battery warning, the requirement and its acceptance criteria must first be clear and traceable. Design of all mechanical and electrical interfaces, communication signals, software logic, operator display behavior, and diagnostic responses must then be reviewed. Implementation evidence may include reviewed source code, verified harness connections, approved drawings, and identified software versions. Integration must be demonstrated on the agreed vehicle or a representative integration baseline. Testing must cover normal operation, warning thresholds, boundary conditions, unavailable or invalid battery data, and required regression checks. Test results, defects, waivers, and unresolved limitations must remain visible. Documents, interface definitions, configuration records, and requirement to test traceability must also be updated before completion is declared. This evidence should be stored in controlled engineering systems so the result can be reproduced and audited. If integration, testing, documentation, or traceability remains incomplete, the work is not done and cannot form part of the completed increment. The team must therefore create, review, and maintain this evidence throughout the sprint rather than assemble it only at the end. We have now completed Part 4, Agile Workflows. We explored product direction, product backlog, user stories, sprint backlog, and done increment. Thank you everyone for attending, and I hope you enjoyed this part of the training. See you in the next video.